Alright, so in this video I'm going to be explaining another important article with the title Sparse Structural Learning via Graph Neural Networks for Inductive Document Classification. So this AAAI 2022 article from Korea. So recently graph neural networks have been widely used for document classification. However, most existing methods are based on static word co-occurrence graphs without sentence-level information, which poses three challenges: word ambiguity, word synonymity, dynamic contextual dependency. To address these challenges, we propose a novel GNN-based sparse structural learning model for inductive document classification. Specifically, a document-level graph is initially generated by a disjoint union of sentence-level word co-occurrence graphs. Our model collects a set of trainable edges connecting disjoint words between sentences and employs structural learning to sparsely select edges with dynamic contextual dependencies. Graphs with sparse structures can jointly exploit local and global contextual information in document through GNNs. For inductive learning, the refined document graph is further fed into a general readout function for graph classification and optimization in an end-to-end manner. So, there are three contributions. We construct a trainable individual graph consisting of sentence-level subgraphs for each document. They propose a sparse structural learning model via GNNs to learn an effective and efficient structure with dynamic syntactic and semantic information for each document. So you know how the case iteration of message passing process consists of this aggregation and update equation. So here they aggregate and then they update using the previous representation to update the next representation. But for graph classification, as you know, you need a readout function that aggregates node representation. So you get the readout and then you have a representation for the graph. You know, whenever you see Gumbel softmax, you should know that there is a problem about sampling because, you know, backpropagation cannot just be gone through a sample because it's a discrete, it's a categorical thing. So that's why instead of argmax, we approximate it with something like called Gumbel softmax, which is an approximation, because you know argmax, even if you give it to PyTorch, if it give you an error if it is backpropagating something from downstream. So that's why we use this. Or even, for example, for edge sampling, there is a good paper, neural sparsifier, something like this, that they use Gumbel softmax. Even for variational autoencoder, you have a z variable, you sample it. So there are many cases that you need this Gumbel softmax. It's an important thing. Unfortunately, I don't know anything better than Gumbel softmax to get through the sampling, backpropagation through a sample to make it differentiable. Of course, most authors use this Gumbel softmax technique. So this is an overview. A is the model framework, that you have GNN, then SSL, GNN, SSL, GNN, SSL, and finally the prediction. And in B, you see the local and global joint message passing. And in C, you see the SSL, sparse structural learning, contains dynamic contextual dependency score, and then adaptive sampling for sparse structure. So a document level graph is finally composed of sentence level subgraphs, where edges connect nodes and their local syntactic neighbors, and edges connect nodes and their global syntactic neighbors is. So neighbors of local syntactic are this, and then about the semantic are these. Now, unlike existing GNNs, considering that all nodes are homogeneous, we differently aggregate their neighbor messages by distinguishing the neighbor node types: local syntactic neighbor and global semantic neighbor. To update the node representation, the message passing part can be reformulated like this. A phi is just injective function like relu, and h is just a node representation. So the local syntactic neighbor representation, this one, this is the local static syntactic neighbor representation, is modeled by this, and at the same time the global semantic, this is the global semantic neighbor representation, can be approximated like this. So our aggregation and update is using these, not only syntactic information of the neighbors, but also the semantic information. And because we have two different weights here, we are recognizing them, we are distinguishing them. So they are not entangled, they are disentangled, so no worry. And you see that they just use the information of edges and the representation of previous step, using, because U here is in the neighborhood of your static information, and here Z is the neighborhood of your global semantic neighbors. And then your sparse structural learning. So since a relationship among sentences are not known prior, it is vital to refine the document level graph by exploiting local and global contextual dependencies. One feasible approach is learning from a complete graph where nodes between subgraphs are fully connected. However, fully connected words between sentences usually bring both necessary and unnecessary information, a form of noisy information. Therefore, in this section, we perform a sparse structured learning, which can be divided into two parts: calculating the relative score of global semantic candidate neighbors of each node, which is dynamic contextual representation. Conducting adaptive hard selection for global semantic candidate neighbors using Gumbel softmax. So because they are doing hard selection, what is hard selection? It means you are doing argmax of something, and this is not differentiable. So you approximate it by some kind of softmax, which we call it Gumbel softmax. Finally, global semantic neighbor is updated. So you see that this adaptive hard selection for global semantic is necessary. That's why we need Gumbel softmax. And then for dynamic contextual dependency score, because given a node, we can obtain the neighbor of this global semantic information that contain all global semantic candidate neighbors. So We first calculate attention coefficient score between each neighbor J and node V. So node V has some neighbors. We get the attention, just like if you remember graph attention network, it's similar, almost similar formula. And then you give it to this softmax to calculate dynamic context dependent score. And now sampling based on dynamic contextual dependency score, we perform an adaptive sampling on G star. To determine sparse edge, we set a threshold to select meaningful global semantic neighbors of each node via argmax operation. However, this operation is not differentiable. As I said, argmax is not differentiable. That's why you use this Gumbel softmax here. And then reconstructing sparse graph. Thus, we can select informative neighbors for node V using P. It is worth mentioning that despite P is obtained from S, that is calculating by both existing neighbors and global semantic candidate neighbors, we only select neighbors from the candidate neighbor set to maintain the local static topology of the document graph. Specifically, we update the global semantic neighbors for node V with selected candidate neighbors as follows. So for static local syntactic neighbors, we compute the entropy to preserve consistency of the original syntactic information and prevent too much structure variation in the graph. So at the last iteration, all of the nodes in the graph are fed into this readout. And again, we can have this prediction. So they have some data sets like MR, R8, and you have the number of vocabulary, number of sentences, the number of classes in each data set is different, as you see. And each data set has different number of documents. So we have different categories. It could be word-based, sentence-based, graph-based, and graph-based ind. It means inductive. This is inductive graph. But this is transductive. So to obtain a proper sampling temperature, we set 5 temperatures of each data set. And so during sampling the adaptive neighbors for each node via Gumbel softmax with an adjustable temperature, the smaller temperature, the more samples tend to be categorically distributed, which in our model represents the document graph layering to a more sparse structure.